Hello everyone, we are Group 14 and this is our week 1 status. So this is our team. Manideep will be working on physically building the project. I, Ankit Gomladu, will be working on the PCB design for the same. Rashi will be working on the Arduino code. And finally, Indrasen will work on the CAD design. Our project is to make a motor position and speed controller for a DC motor. We are planning to use the PID algorithm in order to achieve a closed loop feedback system using an encoder. We are also thinking of making a CAD model for a robotic arm and integrate this controlled DC motor as actuator. Manideep will further explain the PID algorithm.
Yeah, so right now the other team as will explain the PID algorithm, but just to go through that, there'll be just a we will set a desired speed, and there is a feedback control system that we're getting from the encoder, and we take that signal and compare it, take the error, and try to minimize the error using type 3 controllers like proportional, integrative, and derivative. Proportional just like takes the error closer and closer to the try to minimize the error, but there is some situations where there will be equilibrium reached and there is no more change due to the proportional one. That is the time when integral comes in and sums up the error over time, sees whether there is a constant error on something, and then uses that as a signal to further decrease error. And there is when you do this integral, when you increase this integral part, there is a possibility that it may overshoot. That like our desired set is 250 and we got to 70 and it has to come back again. So like it will come back of course because the error again increases when it goes to 270, but still we don't want the shoot up a lot because there are some limitations as well in our design. It may be there is some constraints, so we don't want this to happen. So we use a derivative control as well that will just stop control these fluctuations. It makes us a curve smooth. So this is a formula that is used in the PID control. As you can see, this is just this KP and KI and KD are the three variables, three weights that is given to each part, and we have to tune this for every individual system, so that like there are all the random variables like gear ratios and everything will go into this, and we calculate the voltage directly, and that voltage is fed to the L2390 motor driver, and that converts into that is used as a that is used to set the speed of the motor. We're also trying to implement position control as well. And yeah, for position control, we are thinking of using two loops. One is just a just the encoder position, and the second one is also controlling the speed and using those velocity profiles so that it moves to that position very smoothly. Yeah, that's all for the control system part. Let's see how to implement it.
So right now we had looked at a brief overview and the circuit part. So let us look at the PCB design for PID control. So this is an Arduino Nano. It is a small, complete breadboard friendly board and is almost identical to Arduino Uno and differs basically in the number of pins and is of lightweight. Next slide. So this is the encoded gear motor, which is used to measure the speed and rotation angle of the rotor. So encoder is basically a disc which is evenly spaced contact zones that are connected to a common pin C, and there are two other separate pins, contact pins A and B. When the disc starts rotating, the two pins starts making a contact with the common pin and a square pulse is generated by the two pins. So for measuring the rotation position, we can consider any of the pulse, but to determine the direction, we have to consider both the pulse at the same time. Next slide. This is a L29 3D motor driver. As the name suggests, it is used to drive the motors. This is 12. This is the 5-volt voltage regulator. As we know that the Arduino works on the 5-volt supply system. So we supply a high voltage but gets regulated by this voltage regulator. This is the 12 volts DC supply which we used for the power motor. This is the potentiometer. It is used to set the desired motor speed. Potentiometer changes the resistance as we turn, thereby changing the output voltage, which can be used as an input.
So thank you, Rashi. Am I audible?
Yes.
So let's move on to some practical applications for our design. PID control systems are very accurate and they allow precise control over the torque and accurate speed and position control. It can limit the current within a safe limit to accelerate and decelerate the drive at the maximum permissible current and torque. So because of these properties, they can be used in robotic arms, electric vehicles, cooling fans, and CD DVD players. In the coming weeks, we are also planning to design a robotic arm to implement our PID controller. Thank you.